wrap this up real quick before we get to the example. So the note say the Riemann sum, the more rectangles, the closer the sum to the area. So that means if you break it up into very, very fine or the very narrow rectangles, that means the area gonna be smaller and smaller every time. The other way we can say the n, the greater than, so n is approaching infinity, the approximate approaching the exact value. Okay. And since n approaches infinity, the delta x, which is b minus a divided by n, will approach to 0. So that means the bar is very narrow. And at that point, it doesn't matter. You pick the left end, the right end, or the midpoint to find the height of the bar. Okay. So the idea of this is to use the sum of the small rectangles from making a partition under the graph to approximate the area of the curve between the curve and the x-axis. Right. So for this example, we're gonna use key term Riemann sum to estimate the area between the graph y equals 1 over x and the x-axis on the interval a is 1, b is 5 with n equals 4. So we're gonna break it up into 4 equal subintervals. The graph is provided. Okay, that's very convenient, right? So I'm gonna make sure that it's saved. The second. Before I lose it. So for this one, this is the function. I'm gonna put a note. The function f of x equals 1 over x. The point A is 1, the point B is 5, and the n equals 4. So from the graph here, starting from A equals 1 to B equals 5, for n equals 4, that means for any midpoint, left endpoint, or the right endpoint approximation, the delta x or the width of each bar is going to be computed the same way, b minus a divided by n. Okay, b is 5, a is 1 divided by 4. So that means the increment is 1. So it's very nice because the scale already as increment of the 1. So we're going to break it up into 4 equal subintervals. Okay, and we're going to use the first one, we use the midpoint. The midpoint means you're going to identify what is the middle x for each interval. Okay, to find the midpoint here, you can compute like 1 plus 2 divided by 2 or the average of the left and the right end. So for the first midpoint, so I'm gonna draw the real number line here. If this is 1, this is 2, this is 3, this is 4, and this is 5. So my first midpoint here is 1.5, or you can use this at 3 over 2. Okay, 3 over 2. And the next one is 2.5 or 5 over 2. Next is going to be 7 over 2 and 9 over 2. Why I keep it as a fraction? Because it's going to be convenient when you compute the height of the function. So I have 4 midpoint. So I'm going to draw the line here to represent the height of each bar. So that means my first bar with the height of the function at 3 over 2. And the next bar is the same. So use the midpoint to find the height of the bar. Okay. Now we're going to approximate the area. So the area approximately equal to the delta x as the width, because they all share the same delta x. Get the width delta x, delta x. But the height depends on the function value at each midpoint. So these are midpoint value for each of the interval. So the area going to be the width times the height, right? For the height of each bar, the first bar, the height is the function at 3/2. Second bar, the height is the function at 5/2. Next, the function at 7/2. And the last one, the function at 9/2. So the area, the area is approximately equal to the delta x equals 1. So equals 1. And the function at 3/2, the function is 1 over x or 1 over 3/2, 1 over 5/2, 1 over 7/2, and 1 over 9/2. And basically, it's the reciprocal of the fraction. So I just rewrite it, I just flip it. Going to be 2/3 plus 2/5 plus 2/7 plus 2/9. And I just have to add these numbers all together. All right, so let's do that real quick. You can use the graphing calculator or the Desmos.com, either one. So if I use the Desmos, so I do it real quick. 2/3 plus 2/5 plus 2/7 plus 2/9. So I have 1.5746 as the approximate of the area using the midpoint. Okay, depends on how many decimal places the problem asks you to leave. So right now, let's keep it as 4 decimal places. Okay, so this is the first one. It's called the midpoint approximation. So we use the midpoint as the height of the bar. And we have to make a list. What are those midpoints that we're going to use to calculate the height of the bar? All right. And then for the next one, the left endpoint, we use the common information that the function is 1 over x. The delta x is the same, which is from b minus a over n that we computed to be 1. But this time we're going to use the left endpoint. The left end means from the list that we have, I'm going to put the note over here. The first one, as we have the 4 equal subintervals, 1, 2, 3, 4, 5. We're going to use the left to compute the height of the rectangle. So we're going to use the first left, second left, third left, and fourth left, not the last one. And for the graphical way, since we make a partition, the 4 equal subintervals, 1, 2, 3, 4, 5. Yeah, sorry. So not the last one either. So I went overboard. 1, 2, 3, 4. So up until here. So for this one, it's the same. We're gonna erase. So we just need to approximate from x equals 1 to x equals 5 and make it into 4 equal subintervals using the left endpoint. So the first left is when x equals 1. So I'm gonna make the construct the bar with the height from the function of the left endpoint. And the next one, my left end is x equals 2. The next bar, my left end is 3. And the last bar, my left end is 4. Okay. You don't have to compute the middle value. It's easy. You just take the left or the right. And now your goal is to approximate the area. Approximate the delta x as the common width of each bar. Right, the delta x multiplied by the function at each left value. The function at 1, the function at 2, the function at 3, and the function at 4. Okay. And the delta x is 1 as we computed there. Multiplied by the function at 1. The function is 1 over the input, so it'll be 1 over 1. The next, the input 2 can be 1 over 2, and then 1 over 3, and 1 over 4. So you just work on adding the value 1, 1/2, 1/3, and 1/4. Okay, you can use your calculator and check the number with me. So I'm using my Desmos on my end. So 1 plus 1/2 plus 1/3 plus 1/4. I have 2.0833. Okay, so 33 repeating. Actually, there are more decimal numbers after this. As you compare the left endpoint and the midpoint approximation, the left endpoint has higher value. In this case, why is it giving you more value? Because every bar you gain extra area here, where the midpoint you gain and lose at the same time. It's kind of adjust each other, not too much of the error that occur for each rectangle. That's why the value of these two are different. And from the picture, you can see this one is the overestimate. Why overestimate? Because you gain every time. You gain the extra or additional area every time when you move along along the graph. Okay. The next one, the right endpoint, same manner. So the right end this time sharing information that f of x is 1 over x, the delta x, which is b minus a divided by n, computed to be 1. For the for the right endpoint, starting from a equals 1 and then keep going for 4 equal subinterval. For each interval, you're gonna take the right one. So you take the right endpoint of each subinterval. So therefore, the first one is not used. Okay. From the graphical way, so you start from here, stop here, and break it into 4 equal subintervals. For each bar, you know that the delta x is the width, right? The delta x, delta x, delta x. And then we're gonna use the right end. So that means the right end of the first interval gonna be over here. So we're gonna use that to represent the height of that bar. So that's the area that we're gonna use from the first interval. And the next gonna be another right end function value and right end function value, right end function value. So each bar you take the right end. So that's why the first one is not used. And the area, when we set it up, the area is approximately equal to the delta x as the common width of each bar multiplied by the function at the first right, the next right, and then up until the last right endpoint. The delta x is 1. Function at 2 is 1 over 2. Function at 3 is 1 over 3. And then 1 over 4, and then 1 over 5. And then we can compute the area by adding 1/2, 1/3, 1/4, and 1/5. And that will be 1.28 and 3 repeating. Okay, for this situation, if you compare with the right endpoint, it's lower than that number. And from the graph that you look at, you lose every time. Like the rectangle that you form is less area. It has less area than the actual area graphically. As you see, you lose every time. So this one, for this situation, is called underestimate. But the graph gonna help you determine whether it's over or under. Okay, so overall, comparing 3 ways of approximation, and these are called Riemann sum, okay, to estimate the area between the curve and the x-axis. You can see that the midpoint will give you the most reasonable approximation.